Here's the announcement slide for where we're at today. The next homework assignment will be due a week from today. I don't have one. You need to do that before you come to class. And we're going to be talking about non-circular conduits and local losses today. A lot of pipes that we'll use are non-circular. It's pretty common to use circular pipe in a municipal water distribution network, but if you've got a culvert, it's pretty common, especially for large culverts, for the pipe to be non-circular. You can see that this is an elliptical pipe arch. And this is a picture that I took when I was teaching in the UAE. It's runoff flow that's coming out of the mountains, and it doesn't rain very often there, but when it does, it's really an enormous flash flood. And for some reasons that we talk about in hydrologic engineering, you really don't want water going over the top of the road, at least not for too long. It's okay for storm flows to overtop occasionally and for a few minutes, but if there's overtopping for too long, it could actually wash out the road entirely. And so you want to make sure that there's a big enough cross-sectional area for flow to go through. And when the water is only partly full through that culvert, then it's not closed conduit flow, it's open channel flow. But then when the water level is very high, when the water level is getting up near to the road surface, then that actually becomes closed conduit flow. You can see the image on the right is some square metal pipe. Not really common, but sometimes it's out there. And so part of today's class is just identifying how we make the substitution for different geometries when we don't have a circular pipe, when we don't have a diameter any longer. So hydraulic radius, which we use in both the Manning's equation, and also it comes into play in the Hazen-Williams equation. Normally, we are going to have, for a full pipe, diameter divided by 4, if we're talking about a circular pipe. But if we're talking about a non-circular pipe, then we just put in the actual wetted perimeter and the cross-sectional area of the pipe. The Darcy-Weisbach equation, if we don't have a D parameter, if we're trying to solve for the head loss using Darcy-Weisbach, but there's no D, you can see down here we had D2G. The substitution that we're making in place of the diameter is just 4 times the hydraulic radius. And that's the same substitution that we'll make everywhere else that there is a D parameter. And that's related to our earlier observation that for a pipe that's flowing full, hydraulic radius is just D divided by 4. So any sort of an enclosed conduit that's flowing full, what we can do as a substitution, we'll say that D is going to be the 4 times the hydraulic radius, R sub H. All right, so that's what's been done here. Reynolds number, similarly, this is the full version of the Reynolds number where we have separately accounted for the absolute viscosity and the density of the fluid. This abbreviated version of the equation, where did I calculate? Okay, here. So if we were using this version of Reynolds number and we didn't have a circular pipe, then we just make RE is equal to 4 times velocity times 4 times the hydraulic radius divided by the kinematic viscosity. So we just drop R sub H, 4 times R sub H in place of the diameter that would ordinarily be there. So you get the idea. With relative roughness, instead of epsilon divided by D, it's epsilon divided by 4 times the hydraulic radius. All right, so let's consider the case of a box culvert. These culverts that I showed you earlier are pipe arches, but sometimes it's common just to have a concrete box used as a culvert. So let's assume that we have one of these concrete boxes and it's flowing full all the way. And we want to know what's going to be the head loss for the flow conditions that are described there. So I'd like you to work this one. You can go through the steps with a partner. We're going to, since it's full flow, use the Darcy-Weisbach equation. And here's the Jane equation that's been modified. Instead of K sub S divided by D, you can see that it's K sub s, which is just another variable for epsilon. That's the equivalent sand roughness of the pipe material. K sub s divided by 4 times the hydraulic radius. Okay, so the steps that you'll need to go through are kind of laid out in the equations that you start here, then there, and so on. So I'll pause the recording and give you a minute to try and calculate the head loss. Okay, we start off with the geometry, just finding the cross-sectional area. Since this is a square pipe, it's 1.25 by 1.25, so we get the cross-sectional area is 1.56 meters squared. The wetted perimeter is 5 meters, and remember that the wetted perimeter is just talking about what is the length that water is actually in contact with, and so for us that's going to be all 4 sides of that square shape. So the hydraulic radius is 0.3125 meters. Using Q divided by A, we find the velocity is 0.256 meters per second. Substituting into the modified formula for the Reynolds number, now here I'm writing the Reynolds number in terms of absolute viscosity and density. We can also do it in terms of kinematic viscosity, but the Reynolds number is 320,000. Okay, so we're going to use that 320,000 when we substitute in all the given information and what we've calculated so far into the Jane equation. You know, the other approach is that you could look this up off of the Moody diagram. But on the Moody diagram, you wouldn't be able to calculate it to this level of precision. Okay, so the F is 0.0218 for the friction factor under these conditions. And then finally we substitute that into the Darcy-Weisbach equation and get only 0.0007 meters of head loss due to pipe friction. That's not a very exciting result. I should have changed the numbers around so there's more head loss or something. But the fact is that there's not very much head loss due to pipe friction through a large box culvert like this. Most of the energy loss that occurs is actually due to water flowing into the entrance and turbulence as it exits. In a box culvert, the local losses are pretty significant. Whereas, because it's so short, you know, it's only 12 meters long, there's not going to be a lot of pipe friction losses. Okay, any questions about this idea of how to approach a non-circular conduit? All right. Well, let's talk about local losses then. And remember, I previously have said that kind of the pejorative term for local losses is minor losses. And we don't use that term because it implies that the losses aren't important. And usually that's true. But there are cases, you know, really important cases where the local losses, if you neglect them, you're going to get a really bad estimation of what the pressure is, or a bad estimation of how much loss has occurred from one place to another. These local losses occur at fittings, like here you can see is a 90-degree elbow, at transitions like a pipe diameter change. And what's shown as the equations here are how you calculate the local loss at a single point where you have the same velocity entering this transition as exiting the transition. There's just a change in direction, and how much turbulence is induced by that change of direction is going to inform what K value is used to calculate the loss. It's a little bit different on how changes in diameter are described, and in fact, depending on the manufacturer's data that you get, sometimes the head loss should be calculated just based on the entrance velocity multiplied by some K value. In other cases, they've calibrated the K values relative to the difference in velocity through the transition, so that a small difference in velocity means that you have a small diameter difference and there's not going to be as much energy loss. The bigger the differential, that's going to introduce a lot more turbulence. If it's a small pipe going to a large pipe like this, obviously you're going to have the water here moving very slow, but then the water here is moving extremely quick, and there's just a jet of turbulence as it enters that pipe. It's almost like a water going into a tank, in which case it loses the entire velocity head when water transitions from a pipeline into a tank. And so a really extreme transition in diameters is essentially the same thing. We'll look at some K values on the next couple of slides. What this accounts for, though, is just the loss of energy at a point rather than over a length. And when we've been using the Darcy-Weisbach equation and Hazen-Williams, when we're selecting location 1 and location 2, what we're assuming is that the frictional losses are all of the losses that are in between. And it's distributed over some pipe length because of the interface between the water and the metal surface. But here, when we use the Darcy-Weisbach equation and we have location 1 and location 2 in our energy equation, then we would add up all of the local losses in between the two. And they're occurring at points, but it's over some distance between points 1 and point 2. So we need to be on the lookout for pipe entrances, meaning where a water is flowing from a reservoir into a pipe, because there will be energy loss there. Anytime the pipe changes diameter or gets smaller or bigger, there will be energy losses. Anytime the fluid changes direction, or when it flows through fittings like valves or T's or elbows. So let's look at some of the tabular information that comes out of your text. First of all, it's talking about the change in pipe diameter. And so let's try and identify what is the trend. Here is a couple of different columns here, and what these angles are referring to is how gradual is the transition. The angle that they're describing here, when it's just an abrupt transition like I've drawn here, there's going to be more energy losses than if it's a 60-degree angle. And by 60-degree angle, that's more of like what's pictured here. You see that it's sort of a gradual transition. And so why is it that if the diameter 2 to diameter 1 is 0.2, so that means that diameter 2, this is a contraction that we're looking at for now, that ratio means that here's diameter 2, here's diameter 1. If the ratio of D2 to D1 is 0.2, then that means that the diameter here is just 20% of what it was upstream. So if we're looking at here, then we'll have a K value of 0.08 for a 60-degree angle, and you can see that's a pretty smooth transition compared to 0.49 if it's just the 180-degree abrupt transition. So you're losing a lot more energy when you don't have this gradual narrowing down, and instead it's just big pipe instantaneously and small pipe. Having the transition kind of guides the flow and helps to avoid too much turbulence. So you can see each row is a different ratio of downstream diameter to upstream diameter, and then it gives you an idea of the effect of having a smooth transition versus an abrupt transition. Eventually, if it's close enough, if you've got 90% similarity between the diameters, then the K values are pretty small. So you can see that the other trend that is identified in this data is that the closer together the diameters are, the smaller the K value, which means there's going to be less energy loss. And that kind of makes sense, that if we have a really big transition, then that'll induce more turbulence. And then kind of the reverse is true on the expansion. Having a gradual expansion, these K values are lower than having an abrupt transition. So that makes sense because we're avoiding turbulence. And then here it's listing some of the different valves that we can encounter in a flow network. And I've got some diagrams of the valves. We'll look at them in a little bit more detail. This last row of data is talking about how sharp a transition is, the radius to diameter for a bend. And we saw this on the pipe rack last semester, that one of the bends is very long and gradual for changing the pipe direction. But then there was another bend that was pretty abrupt. And so by radius, what we're talking about is this distance out to here. That's the R that's described in this bottom table here, R. And then the D is referring to the diameter of the pipe. So what you need to do when you've got a transition like this is consider how long is the radius relative to the diameter of the pipe. And so now here are the K values. And it's kind of interesting that you'd expect a really long gradual transition to have the lowest K value. You want it to be a really slow gradual transition, not all of a sudden abrupt changing, because if it's abruptly changing, you're losing more energy. But look how what we would expect is occurring at first, that as the R to D gets bigger, meaning that you've got a long radius relative to the diameter, the K value is coming down, and it's going down again, but then it starts to increase again. So any guesses on why all of a sudden you'd start losing more energy after making that transition more gradual and longer? Exactly right. Yeah, it's just that it's longer. It's not that it's more gradual is somehow inducing a greater loss, but what they're sort of combining in here is the effect of the local loss and the frictional losses over the course of that transition. So the gradual increase again is essentially friction and local losses built into the table. So it looks like sort of from this standpoint, the optimal radius relative to the diameter is 4 if you want to minimize energy loss in a transition. Mm-hmm. Yeah.
Isn't that saying basically
Yeah, it is. No, there's still water flowing. We have the case of water coming out of a tank, and what it's showing is if you have an infinitely large origin and a small pipe, that's sort of like that top row there where it's saying 0.5. So what they're saying is that when you have water coming in from a tank to a pipe, then the K value is 0.5. And then you take that K value and multiply it by the velocity head, v squared divided by 2g. So whatever the velocity is through the pipe, just even as the water is going into that pipe, then it would be 0.5 times v squared divided by 2g. And then the other thing that you noticed here, in this one, it's saying 1. And so if you have the pipe exiting into a tank, then what that is implying is that in that exit, you're losing 1 times the velocity head. And so that means all of the velocity, all of the energy that's in velocity, when the water discharges into the tank, that energy is just instantly lost. And so both of these, both the contraction and the expansion, where it's the d to d is 0, are on another slide showing that in greater detail. But I'm glad you asked about it. It's taking it to the limits, I guess, to the extreme. Different types of valves cost a different amount of energy. And you need to start thinking of, like, pressure is a currency. And you'll really get into that idea when we do the project. During the project in this class, you're designing a municipal pipe network, and you're trying to figure out how big should the pipes be. And what you're going to be deciding is you're going to be balancing. If you make the pipes big, then the system costs more money. But if you make the pipes really small, then people don't have very much pressure at their house. And so, like, there's this range of acceptable values that you're trying to balance, where you want to make the system as cheap as possible but also deliver required pressure to different houses. And so when you are thinking about how much pressure do I need to deliver to someone's house, you have to think about what sorts of valves are used in a home. And if you have lots of globe valves, for example, you can see that the K value for a fully open globe valve is 10, which means as water flows through that valve, even when it's all the way open, you're losing 10 times the velocity head. That's a lot of energy to be lost, especially when you compare it to a gate valve, which is basically just like there's a metal plate in the way that you can move it out of the way. So the water flows through a pipe segment completely uninhibited, just a little bit of turbulence it's picking up off of the edge of that gate. That, even when it's out of the way, the water's sort of banging off the side of that gate a little bit, so you've got a K value of 0.15 when it's fully open. But the water that's flowing through a globe valve really has a pretty circuitous path where it's changing direction several times. I've got a zoom in of what a globe valve looks like and why that K value is so high. In just a minute, we'll take a look at that. So you can see here some other types of valves. A ball check valve. You see the K value for a ball valve is 70. And a ball valve is a little ball that, as the water is flowing with enough pressure, it pushes the ball out of the way, but when the pressure is too low, the ball will drop and cover the opening. But it's just that as water has to flow around that obstacle, it causes a lot of disturbance to the flow. You can look up these K values from the manufacturer specified tables, and we'll pull open an example of what a manufacturer K value table looks like. But here's that entrance and exit loss K values that I was talking about when we were discussing the infinitely large pipe on the upstream end. So if you have just a rectangular edge to a pipe transition where water's coming from a tank and entering the pipe, then it says a typical K value for that is 0.5. If you don't miter that pipe to the edge of the tank, though, if you just have the pipe entering the tank like this, then the K value is higher at 1 for the entrance loss. And so if you smooth it out and try and avoid too abrupt a transition, then you can knock the K value maybe as low as 0.04, depending on the radius of the bend there. And the book even has a little formula. Who knows how accurate it is, but just estimating the K value depending on the angle that the pipe is leaving the tank. And just this is making the point that you may have more energy loss to an angled exit from the tank than if it's just a straight exit from the tank. You can see that it's starting off with the 0.5 that you'd have if it was straight, and then there's additional losses depending on the angle. Okay, so here's that globe valve that I was talking about, and just comparing it to a ball valve, like think about what's happening to the flow and how is it changing direction as water goes through a globe valve. The water enters in one direction and immediately has to go down and then straight up past a plug, and so you've changed directions twice already. You've got an obstacle in the way, and even if that plug is all the way up and out of the way, it still has to change direction again before it exits. And so that's where you're getting a loss of 10 from. The advantage of a globe valve is that you can really cinch it down pretty tightly, and if this valve plug is made out of rubber, or if there is an O-ring here and the valve plug could be made out of metal, you can have a nice tight seal there. And so, it may be that the globe valve is justified in the energy that you're losing in using it because you need a really tight, reliable connection that a ball valve maybe wouldn't be able to offer. A ball valve is really easy to open and close. What you're essentially doing is you've got a pipe section drilled through a sphere, and when you turn the top handle here, you're just moving that hollowed out pipe section from the sphere out of the flow direction, and so that the water that's coming in is just running into the leftover metal or plastic that's in that ball valve. But it can leak around the sides. The water in really high pressures can easily leak around the side of the ball, and so it wouldn't be a really great option if you have high pressure that's coming through the flow. Let's take a look at some K values. Provided by Metro Pumps. All right, so let's compare the globe valve and the ball valve on the table that they've got here. If we were going to use like a 4-inch pipe, the ball valve, it's saying that they can sell you, has a K value of just 0.05, whereas the globe valve, 5.8. So it's 100 times more energy loss to put the water through the globe valve than it is to put it through their 4-inch ball valve. So you can see that there's a whole range of different fittings that they have available, bends, elbows, and so on.
What does the LD
LD. That's a good question. I'm not sure. Yeah, I don't know. Any guesses? What's the best thing that it could stand for? Make that a contest. Oh, length to diameter. That's what it means. It's talking about how long is the fitting, I think. If it's saying, you've got a piece of pipe that, if it's a 4-inch pipe, let's see. So it's saying the ball valve is 3. So I think what it maybe means is that if you have a 4-inch diameter is the intended ball valve, that then it would be 3 times 4, so it would be 12 inches long, that piece, the physical dimensions. That's my guess. Yeah. That globe valve is 340 length to diameter. I don't know. That could be off. That's how it seems to be they're using L to D here. So. All right, just to finish things up today, we're going to work an example where you're going to be combining the Hazen-Williams equation with these ideas of local losses. Now remember that total energy loss that we put into the energy equation takes into account both friction losses and local losses. So that, let me write the energy equation out in full, including terms that we don't usually take into account. We'll go way back to fluid mechanics and see if we remember what each of these terms means in the energy equation. Okay, so the energy equation says that the pressure head at 1 plus the elevation at 1 plus V1 squared divided by 2G, and we have an alpha in front of that, plus HP is equal to P2 divided by gamma plus Z2 plus gamma alpha V2 squared divided by 2G plus HT plus HF plus H naught. All right, so first of all, does anybody remember what that bar above V1 and V2 means? It's implied when we usually use it, but what is it? Average velocity, right. Because remember that in a pipe, there's a whole range of velocities. At the center of the pipe, the water is moving more quickly than the edge of the pipe. And so usually we don't bother to put that bar over the top of it, but it's implied. What we mean is the average velocity. All right? So I'll just erase that. I just wanted to re-emphasize that it's the average velocity we're talking about. What about the alpha that's in front of the velocity head term? It's a coefficient of some sort, definitely. It's the kinetic energy correction coefficient. And what it is related to is actually the velocity distribution. Again, what it means is that, let's say, for example, if you had laminar conditions, then the velocity profile is bullet-shaped like this. And if you use the average velocity in the velocity head term, when you have laminar conditions, then that would actually undercount how much energy is in the velocity head. And so when you have laminar conditions, then you're supposed to use an alpha of 2.0. But when you have turbulent conditions, you're supposed to use alpha is 1.05, because average velocity is a better estimate of the velocity at most locations in the pipe when conditions are turbulent. What I hope you remember from the lab last semester is that laminar flow in a pipe is actually very rare. It's not very common that the water is moving slow enough for conditions to be laminar. So it's so unusual for you to have laminar flow that 2.0 isn't going to happen very much when you're applying the energy equation. And then the other sort of, I don't want to call it lazy, but it's a simplification, is that 1.05 is close enough to 1 that we usually don't bother with alpha unless we have a really, really precise modeling that we're trying to do. So I just wanted to re-emphasize and remind you about those. We'll erase it for now. We won't bother to put in 1.05 in this example. Okay. Now what about HP? What does that stand for? It's energy added from a pump. And in this, when we're going from 1, where the pressure is 650 kPa, that's location A. Location B is 2 in the energy equation. There's no pump here, so we can cross that out. There's no turbine, and turbine has to be on the right side of the energy equation when our notation is that water flows from 1 towards 2. Since there's a direction assumption in the energy equation, that's why we put the pump term on the left side and the turbine term on the right. There's no turbine either, at least in this example. But we do have local losses and energy losses. So what you're going to do is you're going to use the local loss equation along with all of the K values that are specified along the way. It looks like there's 3 different fittings, a pretty sudden pipe bend, a globe valve, and then a more gradual pipe bend with a lower K value. So you'll need to calculate what is the velocity head at inside the pipe, because the diameter of the pipe is the same through all of those. If you had different diameters and different velocities, then you'd have to keep track of it separately. But in this case, this summation term here means that if you've got the same velocity for all 3 of those local losses, you can just add up the K values and then multiply that summed up K value by the velocity head one time. So we use this to calculate the effect of the local losses, and here is the Hazen-Williams equation expressed in terms of energy loss due to pipe friction. All right. So work on this with a partner. I'll give you 5 or 10 minutes to get a head start on that, and then I'll begin writing the solution on the board. So the water is flowing through this pipe from A to B, and what we've said is let's have this location A be our elevation datum so that all elevation is measured above this location. So ZA is going to be 0, and that means that ZB is going to be the 12.5 meters higher that's mentioned in the problem statement. So the question is where is the energy going that exists at A? There's 650 kPa, and that's where the energy is coming from that's going to be used up by pipe friction and local losses, and then whatever's left over is what's causing the pressure at B. That's why there's some certain amount of pressure at B. However much pressure there is at B is dictated by what losses there were along the way from A towards B. So the pressure is gradually decreasing the whole time the water is flowing through that pipe. It's decreasing because of pipe friction, because of these local losses, and then also because of the elevation change. There's the hydrostatic effect that the energy equation automatically takes into account. one of the simplifications that we can make in applying the energy equation is that since this pipe diameter is the same between A and B, that means that V1 and V2 are equal. So you wouldn't get the wrong answer if you leave the V term, the velocity head term, in the energy equation, but it's not necessary since V1 squared divided by 2G is equal to V2 squared divided by 2G. So that's why I've canceled them out.
So if the pipe wasn't continuous or the same diameter,
Yeah.
we would just use this equation 3 different times for 3 different pipes.
Exactly. Yeah, let's say that, you know, right here the diameter was, do I say what? Yeah, 350, and then here maybe the diameter is 500. You'd have to solve the continuity equation each time to find out what is the velocity there, and then you'd multiply that localized velocity by the K value for that location. Yeah. And then, you know, if it was a different diameter here than there, then you couldn't cancel out the V's like I have as well. You need to keep the velocity head term in the energy equation. All right, so this is where all the energy is coming from, is the pressure head, 650 kPa divided by 9.81 kilonewtons per cubic meter. You can also write 650,000 newtons per meter squared divided by 9810 newtons per meter cubed. That works out to this, the 66.259. That is the pressure head that there is at 1. What that means is that if we punctured the pipe right here and put in a piezometer, the water would rise to a height of 66.259 meters. Now that's not an imaginary value, that has physical meaning, that pressure head. So we rearrange the energy equation, and you can see that having solved the Hazen-Williams equation for pipe friction losses, we get that it's 43.107 meters is the amount of friction losses. By the way, one thing that I should point out is this 4 meters per second, that's above the limit allowed for the Hazen-Williams equation. So we're sort of straying from what it's intended, and so that introduces an element of uncertainty in our solution. Most likely, this is going to overestimate how much energy loss there is, since we've gone above the 3.5 limit. I mean, it doesn't mean that the equation and its output is completely meaningless. It just means that the further you are from the intended constraints, the worse your results are going to be. Putting in the sum of the K values, 10.4, and multiplying that by the velocity head, we get that the local losses are 8.481 meters. So this is the energy that there was at A. 66.259 meters of energy was there. We lose 43 due to pipe friction, 8.48 due to local losses, and we lose 12.5 because of the elevation change. And what's left over, there's 2.171 meters of head at B, which yields a pressure of 21.3 kPa. That's not enough. Most municipal networks have an absolute requirement that even during a really high water flow, like if there's a fire in an area, the pressure still has to remain above 140 kilopascals, because if the pressure goes too low, then water can start going back into the pipe network, backflow. Like, you know, if you're at the top of a skyscraper and you open your faucet when it's low pressure, then the water, instead of coming out of the faucet, would go from your pipes back into the distribution network. And so that's not good, obviously. There can be contamination and the water quality can suffer if the pressure gets too low. So this 21.3 would be problematic, and we'd need to put in a booster pump, or we'd need to get a larger pipe diameter. There's a number of things that, as a hydraulic designer, you could do to try and increase the pressure at that downstream location B. That's a good question. That globe valve lost us most of the local losses. So that would get us probably like another 8 meters of head, which works out to like roughly 8 times 10. You know, we get 80 kilopascals out of that. So that would get us to 100. We'd be most of the way there, but not quite all the way if we wanted to be at no less than 140. Okay, so remember that when we get together in class on Thursday, we're going to be playing around with Excel. So if you've got a laptop, bring it. And if not, come a little early so you can log on to the tablets and it can load your profile and all that stuff. I will see you on Thursday.